Yeah. So for today's live discussion, I'm planning to cover contents in roughly 3 lectures. Obviously, the first and the third lectures are a little bit major, and therefore we will see a little bit in detail. But the lectures by themselves are quite descriptive. So, but anyway, I will just quickly go through these lectures, and with that we will complete. And the remaining lectures are all from the same topic, that is electronic spectra and electronic properties. So we will see all of them together in the next class, which will be on 22nd November, and that is likely to be your last class. Okay, last lecture class. So after that, we will discuss and then find out time, if time permits. If you all have convenient time slots, we can have one more quiz before the final exam. Okay, so that's the plan. But anyway, that I will coordinate through the maybe 29th. We can have a quiz if all of you are available. Okay, and your final exam, although you will get a email from 1 second. Okay, now this topic is called isolobal analogy, and as I also told you, what is isolobality? Isolobality is where you have two groups which can be compared, with respect to their orbital symmetry. Okay, so just 1 second, just give me time. Yeah, so am I audible now? Hello.
Yes, sir. Yes, sir.
Yes, sir. Yes.
Yeah, so isolobality is where you try to find out two groups which have similarity with respect to their orbital symmetry, as well as when you say orbital symmetry, you are talking about the frontier orbitals. Now, what are frontier orbitals? These are the orbitals which are in the higher energy, like typically HOMO and LUMO. That's what we call it as frontier orbitals. Now, why do we consider only frontier orbitals? Because it is these frontier orbitals which actually participate in a reaction, right? So rest of the orbitals do not participate, only the HOMO and LUMO. Either most of the reactions, if you see, either HOMO accepts electrons or donates electrons, or LUMO accepts electrons. Okay, so it is that's how the reactions happen. So therefore, the frontier orbitals are very important. And what Roald Hoffmann proposed was, depending upon the symmetry and the energy of frontier orbitals in, let's say, between any two groups of molecules, he says that if they are similar, if their orbitals are of similar energy and similar symmetry, then you can compare them. So in English, analogy means comparing. Okay, so you can describe something with an example of another thing. That is called analogy. Okay, so that you can go and find out also what is analogy with an example. So let's say I want to explain an analogy. Okay, let me give a short example. So I want to explain something like an analogy, like say that reaction A is faster than reaction B. Okay, so in order to explain this, I can use an analogy saying that reaction A is like tiger, whereas reaction B is like tortoise. Okay, now these two are analogies, right? So what I'm conveying basically here is reaction 1 is much more vigorous and faster in rate, whereas reaction 2 is not that fast, it is very slow and sluggish. So instead of explaining all of these things, I just correlated with some kind of an analogy. So that's how in English language we use this analogy. Now similarly here, you can take an inorganic fragment and predicts its reactivity by comparing it with an organic fragment. Okay, now what to compare with? That's where we take the frontier orbitals. If you take the frontier orbitals of an inorganic fragment and then the frontier orbital of the organic fragment, if they are equivalent in symmetry and energy, then we say that these two are analogous. Okay, isolobally analogous. So therefore, analogous is coming from the word analogy, which means that they two are comparable. Okay, so therefore, these two fragments, which are totally unrelated otherwise, can be compared because their frontier orbitals are looking identical or similar. Okay, there can be slight variations in energy, but most likely the symmetries are all matched. Okay, so the way they build it, actually, as I also acknowledged, this is based on the NPTEL lecture by Professor Samuelson. So if you want to look at the original lecture, you are most welcome to go and have a look at it. But I've even taken the slides from there. Okay, so I'm just giving you the reference so that if you want, you can go and have a look at it. Now, the way, why do we need this is basically, let's say that in organic chemistry, which most people find it easier to understand, especially the reactivity part. And when you say, let's say this kind of an organic molecule. Okay, now when you have this kind of a molecule, and every point you know that it has got a hydrogen and hydrogen atom. Now, if I'm going to break one of the CH bonds homolytically, I will create a carbon radical, and also I create a hydrogen radical. Now, once I remove this hydrogen radical, I can in principle satisfy the valency of the carbon radical by attaching any other radical. Okay, it can be an oxygen radical or it can be a methyl radical. When I say it can be propyl radical or isopropyl radical, it can be a very big even phenyl radical. It can be any radical. All you need is one radical here whose energy and the symmetry of orbitals match to that of the carbon atom. That is all we need. And in organic chemistry, we know that it is easy to replace that hydrogen radical with an alkyl group or let's say a phenyl group or aromatic group or anything. Similarly, when I remove two hydrogen atoms, then you create a biradical. And that biradical can also be replaced either with two alkyl groups, or you can put one oxygen, which will form a ketonic group. Okay, so that's how we easily identify in what directions the reaction will proceed. And these kinds of intermediates and then analysis are also extremely useful to write the mechanism of reactions. How do you make, let's say, ketone from a hydrocarbon? Okay, so basically mechanistically what you do is you remove two hydrogen atoms as radicals and then you attach one oxygen radical, you get a carbonyl group. So that's how we understand organic chemistry. And that is the reason why we understand organic chemistry, is that we know that when you remove a hydrogen radical, it is equivalent to replace another group, which is also a radical, like a methyl group or a ketone group. Okay, which is also a, when I say ketone, it is an oxygen radical. So, so therefore, we are, and I mean, without realizing, we have introduced some analogy into this concept of organic chemistry, where we are saying that an R group is analogous to a hydrogen group. A hydrogen group is analogous to an oxygen group, right? So because these are all interchangeable whenever you do a reaction. So that is what is, you systematize this entire organic chemistry by understanding it in terms of their structures. So when you go deeper, then actually you find they are all analogous because their frontier orbitals are all equivalent. Okay, so that the same thing is what they extended to organometallic chemistry or inorganic chemistry. And they said that even in organometallic chemistry, you can determine the frontier molecular orbitals of an inorganic fragment. So they, let's say that you take a ferrocene or a cyclopentadienyl ion. I can break any of the bonds homolytically and then create a fragment. Either this can be a fragment, which is a purely an organic fragment, and this can be another fragment, which is an inorganic or organometallic fragment. And similarly, I can also create another organometallic fragment, like in this blue color. Similarly, another organometallic fragment in this titanium compound. Now, these fragments, if you take the frontier orbitals and compare it with any of the organic fragment with similar frontier orbitals, then one can bring about a lot of understanding of how these fragments will behave. Okay, and surprisingly, their behavior is very, very closer to that of the behavior of an organic fragment with the similar frontier orbitals. Now, all of these things happen because it is the frontier orbitals which actually is leading to the reactivity. So now in this, how we start the lecture is, let's say how you start understanding this concept is, you take let's say a octahedral complex, and then let's say you break one of the bonds with a metal ligand bond. Then what you essentially create is a pentacoordinated system here. And then if you break two bonds, then you create a tetracoordinate system. If you break three bonds, you create a tricoordinate system. If you break four bonds, then you create a dicoordinate system. And all of these red ones are all called inorganic fragments, right? They are all fragments. They are not a complete molecule. They are fragments because they still have valencies that are unsatisfied. Now, if you take a methane molecule, or let's say in this case, a methyl radical. Now, what is the connection between the methyl radical and one of these fragments? Is that methyl radical also has one valency missing. Otherwise, it would have formed methane. Similarly, CH2 has two valencies missing from methane. And similarly, in CH is also missing three valencies from that of methane. So therefore, all of them are related to methane by missing one valency, right? So therefore, all of them can, in principle, be related to one of these fragments. Let's say this fragment, let's say methyl fragment is equivalent to this fragment, because in this case also there is one valency missing. In this case also there is one valency missing. Okay, when it comes to CH2, there are two valencies missing. Therefore, this is equivalent to this fragment where two valencies are missing. Similarly, CH triple bond is having three valencies missing, and therefore this is equivalent to this one. The reason is that all of them want to go to octahedral complex, and here all of them want to go to methane molecule, and therefore there is some connection between the number of valencies missing. Now, valencies missing is equivalent to the reactivity in chemistry, and therefore the reactivity is again connected via frontier molecular orbitals. So what we go on to do is to find out how to draw the frontier molecular orbitals for these fragments, and then see how is the connection made. Okay, now if you take a simple metal complex, you have 5 d orbitals, you have 1 s orbital and 3 p orbitals. Now, in a typical complex, what happens is that the 3 T2G orbitals remain as non-bonding. If you go back to your sigma only complexes, you will understand that the 3 T2G orbitals will remain non-bonding, because in your ligand group orbitals of sigma only complexes, you will normally not find ligand group orbitals with symmetry T2G. So therefore, they do not participate in bonding. And when I say T2G, it is basically d orbitals, right? It is a dx, dy, dz. So therefore, what we are essentially talking about is a number of d electrons. Now, the rest of the orbitals in the metal, they all are ready to form a bonding molecular and anti-bonding molecular. I mean, they're all grouped into certain symmetry labels, which we call it as a metal group orbitals. Similarly, the ligand group orbitals also come with its own set of labels. And therefore, all of these things will find matching symmetry with the ligand group orbitals. Therefore, they combine to form bonding and anti-bonding, which is what is shown here. In this lower figure, you will find this is non-bonding, and this is anti-bonding, and the bottom one is a bonding. Okay, so usually the ligands come with 12 electrons, and therefore all the 12 electrons usually fill up the bonding molecular orbitals. And the remaining one, if all the d orbitals, which are T2G sets, if they are completely filled, then you get 18 electron complex, which are very stable because all your bonding molecular orbitals are filled. And sometimes less than 18 electron complex are also stable, because less than 18 means the number of electrons in this T2G set is not complete. Okay, it is not 6, it is less than 6. But that does not affect the stability of a complex, because these are non-bonding electrons. So therefore, less than 18 electrons can also be stable. Now, more than 18 electrons are also sometimes stable, because if this energy gap is very low, then more than 18 electrons can also be stable. But then majority of the complexes will follow the 18 rule, because this energy gap is quite large. Okay, so that's what we had studied in the past. Now let us see what happens further. So far, any questions? Any questions from any of you? Okay, now if you take a complex, okay, now let me take a complex in which one of the ligands is removed. Then what we have created here is an ML5. Okay, so what essentially it means is that one of the orbitals of the d orbitals is not going to participate in bonding. So originally we had 6 orbitals here. Now one of the orbitals is not going to participate in bonding. So therefore it is this orbital which will remain non-bonding. Although the energy is still higher than the T2G set, but this orbital is not going to participate in bonding because we have removed that ligand. Okay, ML bond is broken now. So therefore this will also remain non-bonding. So what will happen is that there are L5, there are 5 ligands, and there are therefore 5 orbitals of the metal will participate in bonding to form 5 bonding and 5 anti-bonding. 5 ligands will bring in 10 electrons, so therefore all 10 are filled here. And therefore this is your frontier molecular orbital. So your frontier molecular orbital will look something like this. Okay. Now, if any other organic fragment which is similar to this symmetry, then that will have a similar kind of reactivity to that fragment. So that is what is iso-Lobel analogy. Let me see that. Yeah. So in this, they are basically comparing it with the frontier molecular orbitals of MnCO5 D7 system, where you have 3 T2G set, and this is 1 orbital which is not participate in bonding, therefore remaining as non-bonding. Now this is compared to that of a methyl radical which has got iso-Lobel. It is, see, both of them, if you compare, they are not structurally same, they are not electronically same, but they are similar in their frontier orbitals, and therefore MnCO5 fragment is iso-Lobally analogous to a methyl fragment. Okay, so that is what is iso-Lobel analogous. Now, what is the advantage of doing this analysis? Yeah, see, because MnCO5 is analogous to methyl radical, the reactivities are similar. A methyl radical will undergo dimerization to form ethane. Similarly, MnCO5 also can undergo dimerization to form Mn2CO10. And similarly, an MnCO5 can also react with a methyl radical to form a methyl MnCO5. Okay, so now this reaction is a new prediction, which is otherwise not predictable. So we know that methyl radical can form a bond with MnCO5 because you have frontier molecular orbitals looking for another partner. And that is the core concept. Now you then the further lecture is all about how do we understand with respect to ML4 or ML5, things like that. Okay, so any questions so far?
No, sir.
Yeah.
No, sir.
Did you guys read this or first time you are hearing all this? Yeah, anybody had you go through the lecture? No. Okay, please go through then. Okay. Okay. Now, coming back to the next lecture, I will move to, this lecture iso-Lobel analogy is similar, so you can go through the entire lecture. And finally, when it comes to metal carbonyls, okay, now when it comes to the metal carbonyls, it's pretty much one thing you have to understand is how are carbonyls bonded to the metal center. Okay, so now when you take a carbonyl, it is when you look at the when you look at the molecular orbital diagram of carbonyl, what happens is this: you have the HOMO, which is which has got a filled electrons. Now, if you see that, yeah, so this side is a carbon's atomic orbitals. This side is oxygen's atomic orbitals, and center one is a molecular orbital of carbon monoxide. Now, if you look at the molecular orbital of carbon monoxide, you will find HOMO, which is the highest occupied molecular orbital, which is 5 sigma here. This is more closer to the carbon, okay, than to the oxygen. Okay, so therefore, when it is very closer to the oxygen, so therefore carbon, when it is closer to that of carbon, what happens is that the electron density is higher on carbon than on oxygen? So now that is an important question, because typically when you take a molecule like carbon monoxide, oxygen is more electron negative than carbon. So people would expect that oxygen will have a higher electron density than carbon. So therefore, in metal carbonyls, oxygen should have bonded with the metal. Okay, but then what happens in actual metal carbonyls is that it is a metal that is forming bond with the carbon and not with the oxygen. And the reason is that the carbon has got a more electron density in its ground state than the oxygen. And that is because of the molecular orbital diagram. Now, therefore, in a metal carbonyl, this HOMO on carbon is going to form a bond with metal. And once the electron density builds on the metal, it is going to back donate electrons to this 2 pi, okay, which is an anti-bonding orbital with respect to carbon monoxide. So when the electron density builds on any anti-bonding orbital, you will know that the bond order will decrease, and therefore the carbon oxygen's bond strength will decrease. Okay. So in spectroscopy, you will also know that when a bond strength increases, the vibrational frequency is higher because it's equivalent to the force constant, right? So it is basically dependent upon the Hooke's law, where the frequency of a vibrating spring, it depends upon the spring constant. Okay. In this case, the strength of the bond is equivalent to the spring constant. So if carbon oxygen bonds are getting weaker, it means that the spring constant or the strength of the bond between carbon and oxygen is going to become weaker, and that will represent, or that will show up itself in the infrared absorption spectrum. Okay. So therefore, when electrons are building up on the antibonding orbital, you will find that the carbon and the oxygen bond strength is weakening, and therefore the frequency of carbon and the oxygen will start decreasing. Okay, so this is the overall concept. So whenever your metal carbonyl is formed, the carbon oxygen bond will become weaker depending upon how much is the back donation. So therefore, if you measure the IR frequency of carbon and oxygen in metal carbonyls, that is more or less an indicative of how much is the back donation happening. So with this being clear, you should be able to understand the rest of the lecture. And I have discussed a number of examples, and that you can go and have a look at it. Okay. So carefully have a look at the metal carbonyl. So I've given the stretching frequencies and then asked why is this higher, why is this lower? And then I would have given you a few complex and then asked which one is supposed to be higher, which one is supposed to be lower. There's some of these things, some of you would have studied in your lower classes. But again, since this is a very relevant topic in the structure and properties of molecules, this topic is included. Okay, so go and have a look at it. Okay, any questions so far?
No, sir.
Yeah.
Sir, in case of the isolable analysis between the trans ligands, sir, you have established an analogy between CrCO5 and PT, platinum chloride, PTCl3 minus. Like how we are establishing a relation between those two compounds.
Hafila, can you just repeat once more? I couldn't hear some part of it.
No, sir. In case of the isolable analogous in the trans ligands part, sir, in that case, you have established a relation between that chromium, penta CrCO5. It is related with platinum Cl3 minus. How we are establishing an analogy?
No, how, see, that's what. So some of it needs a very detailed calculation, which we do not show it in the, which we do not study at that level. See, when you are talking about isolable analogy, two things are important. One is the frontier molecular orbitals symmetry. Okay. So therefore, you compare the frontier molecular orbital. A rough way to calculate, to understand the frontier molecular orbitals is based upon the valency, the valencies that are missing. So if you take, let's say, chromium CO3, okay, now this must have come from chromium CO6, let's assume. So therefore it is missing 3 valencies. So therefore you can quickly arrive at the frontier molecular orbital based on the missing valencies. And similarly, if you also take a square planar complex, and that is missing 2 orbitals, okay, now I have to go to the exact example which you said. Now, therefore, you can quickly understand what is the missing orbitals, missing valencies in the other fragment as well, whether it is due to trans effect or whatever. So now, based on this, you can understand that these two compounds are isolably analogous. Now, the second aspect is the energy aspect, which we cannot directly predict. Of course, if it is between two different metals, you can assume that the energies are more or less closer. And otherwise, there can be lots of differences with respect to energy between the metals orbitals and the carbon or non-metals orbitals. Okay, now coming back to your question directly, no, there is, I have not given an explanation about why we are comparing these two things. That probably comes from some other calculations.
Okay.
Yeah.
Yes.
Yeah. Any other questions?
No, sir.
Okay. If there are no more questions, then shall we stop now? Okay, we shall stop now. And please consult and tell me if 29th you guys are free. If not, we will directly see in the final quiz. If all of you are available, both MSc and PhD students are available on 29th, then we will have one quiz on 29th. And I will tell you the syllabus later, but please let me know in advance. I mean, the syllabus is generally other than carbon group, other than a seminar, after carbon group, and exclude the seminar part, the rest of the things, the nitrogen transition metal group and the electronic structure and all this. Okay. Thank you all. Bye.
Sir,
Okay, sir.
sir,
Yes.
sir, few of us want to talk to you separately, sir. Can you?
Yeah, please. Yeah, please.